Okay class, welcome back. Today we are going to discuss how we can utilize atomic structures or properties to relate numerical quantities to the chemical formulas. If I could summarize this video up into one statement, it would be the following objective: that you would be able to explain the quantitative relationship between element composition by mass and the empirical formula of a pure substance. In saying that, let's dive into this video. Just to quickly review and tie our last two lectures together with this one, we have explored the concept of isotopes and utilizing the percent abundance to determine a sample's average atomic mass. We have also discussed how we can take a specific mass of a substance and convert it either to moles or atoms. Finally, we discussed the importance of moles as the universal conversion factor that allows chemists to relate one substance to another. Now we're going to take that knowledge a step farther and mathematically determine the chemical formula for a specific compound. If we remember back to last year, the chemical formula is a representation of not only the individual elements present within a compound, but also the quantity of each element present within that compound. For example, the formula of water is H2O, and it tells me the individual elements present within the compound, hydrogen and oxygen, which are indicated by the capital letters, and the quantity of each of these elements given by these subscripts. If there is not a subscript present, it is understood that there is one of that element. So in the case of water, there is 2 hydrogen atoms to every 1 oxygen atom. Last year, we accepted the chemical formula for a substance at its face value. Now that you are in AP Chemistry, we are going to take a deeper look into this and why the formula is written as so. So in order to do this, we are going to first need to understand the law of definite proportions. This law states within a compound, there is a fixed whole number ratio for each element that determines the quantity of those elements within the compound. So in our water example, this is basically the reasoning why every water molecule has 2 hydrogen molecules to 1 oxygen molecule. One big thing that will come up in a bit that I want you to notice is that the law of definite proportion states that the ratio between elements has to be a whole number ratio. So we cannot have 1.5 hydrogen atoms to every oxygen atom. We have to have whole numbers to represent our subscripts in a chemical formula. Now that we know the components of a chemical formula, we can talk about the 2 kinds of chemical formulas. If we look at a chemical formula CH2O and C6H12O6, what similarities or differences might you conclude? Some of you may think there are less atoms present in the formula on the left than the one on the right, and you would be correct. But this is not exactly where we're getting at with this example. Others of you might think there are 2 completely different formulas, and you would be partially correct. Yes, CH2O is the chemical formula for formaldehyde, and C6H12O6 is the chemical formula for glucose, which in itself are 2 different substances. So if we reduce the formula of glucose to its simplest form relative to the number of elements, it would be 1 carbon atom to 2 hydrogen atoms to 1 oxygen atom, which is the chemical formula CH2O. Well, how can 2 different compounds such as glucose and formaldehyde have the same chemical formula, yet different properties? And if I'm given the formula CH2O, how then do I know if I'm talking about formaldehyde or a reduced form of glucose? The answer to those questions strictly depends on which type of chemical formula is stated or asked for. When it comes to chemical formulas, there are 2 types of formulas: the empirical formula and the molecular formula. The empirical formula is the simplest and most reduced version of a chemical formula. We can think of this formula as giving us the lowest relative ratio of elements within the compound. The molecular formula gives us the exact number of each element within a compound. This formula is not reduced despite the ability to be reduced if needed. So if we look at our glucose molecule, the molecular formula would be C6H12O6, while the empirical formula or reduced formula would be CH2O. With this understanding that the empirical formula is a representation of the lowest whole number ratio of an element within a compound, we can start using our prior knowledge to calculate the empirical formula of compounds. Empirical formula problems are going to consist of 3 steps to solve them. They are as followed. Step 1, convert what is given for each of these elements to moles of individual elements. Step 2, divide the number of moles of each element by the smallest amount of moles present within the compound. And step 3, if the answer in step 2 produces whole numbers for every element, then those answers are your subscript and you are done. If, though, you have a decimal number present after step 2, you're going to have to multiply each element by the smallest number, in which gets all the individual elements to whole numbers. Note, you are going to have to multiply each element by the same number. Once you get everything into whole numbers, then you can use those answers as your subscripts for your empirical formula. Let's work an example problem and see how this works out. A compound that contains aluminum and oxygen has 4.151 grams of aluminum and 3.692 grams of oxygen within it. Calculate the empirical formula for this compound. Our first step is to convert what is given for each element to moles of that element. So I'm going to handle my aluminum first. I'm going to put 4.151 grams of aluminum over 1 and multiply it by 1 mole of aluminum over the atomic mass of aluminum, which is 26.98 grams of aluminum. When I do this, I get 0.1539 moles of aluminum within this compound. Now we're going to do the same thing for our oxygen atom. We take our 3.693 grams of oxygen, put it over 1, and multiply it by 1 mole of oxygen over the atomic mass of oxygen, which is 16 grams. When I do this, I get 0.2308 moles of oxygen. Now we can go on to our second step. Our second step has us comparing and dividing the moles produced from step 1. So I'm going to look at the amount of moles produced of aluminum and oxygen and see that the moles produced from aluminum is less than the moles produced from oxygen. Because of this, I'm going to divide our moles produced in step 1 by the amount of moles of aluminum produced. In other words, I'm going to take 0.1539 and divide it by itself to get 1, and I'm going to take 0.2308 and divide it by 0.1539 and get 1.5. Because we came up with a decimal answer in step 2, we are going to have to go ahead with step 3 and multiply each element by the smallest possible number to make them both a whole number. Just a helpful hint, if something has a decimal of 0.5 or a 0.5 decimal, then you can multiply it by 2 and get a whole number. Also, if you have a decimal number of 0.25, you can multiply it by 4 to get a whole number. In this case, we have 1.5 as our decimal number, so we're going to multiply everything by 2 to get our whole numbers for each element. This gives us 3 moles of oxygen to 2 moles of aluminum. Since each of these are whole numbers and I cannot reduce them into anything simpler, I'm going to use these as my subscript for my empirical formula. This means my empirical formula for this compound is Al2O3. Okay, so that's a lot to throw at you, so I'm going to not go any farther in this video. There's going to be a practice problem video in which I'm going to pair with this video. You can find that in the AP Chemistry Unit 1 playlist, or hopefully see it at the link at the end of this video. Otherwise, keep up the good work in class and see you next time.